G'day team, welcome back to another video on applications of integration. So today we're going to be looking at kinematics in an integration sense. Now we have looked at kinematics a lot before, but we're now going to apply some of our integrals. So far in kinematics, we know for a displacement function s of t, v of t, the velocity function, is the derivative of the displacement function, and the acceleration function a of t is the derivative of the velocity function. But now that we know some integration, we know we can go back the other direction. So if I'm given a velocity function, I can find displacement. If I'm given acceleration, I can find velocity. So there's lots, it opens up a lot more types of problems, and it's going to be really cool to see. So the area under a velocity function that's greater than or equal to 0 for t1 is less than t, which is less than t2, so the times we're looking at, is the distance traveled. And we can represent that by the integral of t1 to t2 of v of t dt. Now that only applies for velocity greater than or equal to 0. Now it gets a little bit different when we're looking at displacement, and we'll talk about that in a moment. So let's find the distance traveled using the velocity time graphs. So looking at this first one here, we're not actually given a nice function for this, but we can still find the area under the curve. There's some nice geometrical shapes. So the displacement, okay, is going to be the area under the three shapes. Okay, so this first one is a triangle, which is 1/2 times the base, which is 2, times the height, which is 10, plus 4 times 10 for the rectangle, plus 1/2 times 4 times 10 for that last triangle. So we've got 10 plus 24 plus 20, which is going to be 64 units squared. Okay, so if you see one of these shapes, it's a bit physicsy. Looks like a physics motion diagram, all right? Making sure that you're just finding the area of the simple shapes. Now, when we get something like this, it's a little bit different. So I'm looking at my velocity function here, and I want to find the area between 2 and 4. So because it's not a nice simple shape, it's got that curve, we actually find the integral from 2 to 4. And that is of my velocity function. So s of t is equal to 1/2 t squared, take 3t plus 11 on 2 dt. All right, so let's have a look at integrating this. So this is going to be 1 on 6 t cubed, take 3 on 2t plus 11 on 2t, and that one's squared. And we're going from 4 to 2. Now, instead of boring you all by expanding out like I did in the last video, I'm just going to quickly calculate this on my calculator. You're more than welcome to have a go as well, just to make sure that you're getting the same value as I am. But once you have a definite integral, it's worthwhile always putting it on the calculator to check anyway. So 2 to 4, and that gives me 15 meters. Okay, so displacement's in meters. So nice and simple that. So pretty easy, just find the area under the curve, another application. Now, a displacement function s of t is the indefinite integral of v of t dt. Okay. Now, the constant of integration plus c has to be included, and it can be found if we know the position of the particle at any time. Now, the change in displacement equals s of t2 take s of t1, or the integral from t1 to t2 of vt dt. So we've got to be careful with displacement and distance traveled. So a way to find distance traveled is to find the area under the graph. So you could graph it, map what's positive area, what's negative area, change signs correctly and add them together, that's fine. Another way is to draw a motion graph. So we need to draw a sine diagram for v of t, which is going to tell us where the object changes direction. Find s of t, integration and constant. Find s of t1 and s of t2, the starting time, end time, and any displacement for t change of direction, which we get from step 1. Draw the motion diagram and find the total distance traveled. So 5 steps there, and we're going to look at those now. So an object P moves in a straight line with velocity function v of t equals t squared, take 5t plus 6 meters per second. How far does the object travel in the first 6 seconds of motion? So let's have a look at what happens when we use the steps. Okay, so we need to find when v of t equals 0, which you can see that's going to be a nice quadratic of t take 3, t take 2. So t is going to equal 2 and 3, positive. So drawing my velocity sign diagram, it's going to look something like this. Now I can't go into the negative time. And if you graph that function, you'll know that it's plus, minus, and then plus. So we can see that change of direction at t equals 2 and t equals 3. So that's step 1 there. Now step 2, find s of t. So the integral, so s of t equals the integral, indefinite integral of t squared, take 5t plus 6 dt, which is equal to 1/3 t cubed, take 5 on 2 t squared plus 6t plus c. So we've got that constant of integration in there. Now, step 3, find s of t1 and t2, which is going to be 0 to 6, and then s of t for change of direction, so s of 2 and s of 3. So I'm going to find s of 0, s of 2, s of 3, and s of 6. So s of 0, if I'm looking at my initial displacement, that's 0, that's 0, that's 0, so I'm just left with c. If I put 2 in there, 1/3, so probably best to do this on the calculator just with fractions. So 2 cubed minus 5 on 2 squared plus 12. Oh, I've got a syntax error. Times. Cool, so that's going to be 14 on 3 plus c. If I put 3 in there instead of 2, 3, and 6 times 3 is 18. I get 9 on 2. And then if I put a 6 in there, 6, and then 6 times 6 is 36, I get 18 plus c. All right, so now I have enough information to draw my motion diagram. So if this is my s of t, I've got, say, 0, I've got, depending what c is, but 14 on 3 is actually smaller than 9 on 2. So I'm going to be moving to the right from c to 14 on 3. So let's go 14 on 3 t. That's so bigger than 9 on 2. Forgot. And 18 all the way over here. 9 on 2 here. So using my locations and my change of directions, I start here, move to s of 2, change directions, and I'm moving to s of 3, and then I'm changing directions, and moving to s of 6. So t equals 0, t equals 2, t equals 3, and t equals 6. And we finish it off there. All right, so now that we've got our motion diagram, now I've forgot all my plus c's down here. Okay, so they are important. And then this isn't 0, this is actually c. So what we want to do is now find the total distance. Now we take the rightmost distance from the leftmost distance. So we do each individual section at once. So total distance, there, distance. All right, I've got 14 on 3t not t, plus c, I don't know why there's a t in there, plus c, minus c. Then my next section is this bit in here, which is 14 on 3 plus c minus 9 on 2 plus c. And my final one is 18 plus c minus 9 on 2 plus c. So 18 plus c minus 9 on 2 plus c. Now you can see all the c's actually cancel out. So I'm just left with 14 on 3 plus 14 on 3 minus 9 on 2 plus 18 minus 9 on 2, which is going to be equal to, so I've got 28 on 3 minus 18 on 2 plus 18, which is 55 on 3 meters, or in decimals, 18.33 meters. All right, so it's a bit of a longer process, but it's still good to see. And then part B, find the displacement of the object. Well, that's just the integral from 0 to 6 of v of t. Now using the calculator, we can do that nice and easily. And we've got v of t is t squared, take 5t plus 6. From 0 to 6 gives me, the displacement and the distance isn't too different in this case, but there is that difference there, so you've got to keep an eye on that. Awesome. Thank you for watching the video, guys, and we'll see you in the next part for a bit more kinematics. See you then.